computer chipmakers are adding more cores or processing units for increasing the computational power. But the problem of communication between cores becomes bigger when the computer chip has more cores or processing units. For years, a Singapore research professor at MIT has argued that the massively multi-core chips of the future will need to resemble little internets, where each core has an associated router and data travels between cores in packets of fixed size. This week at the International Symposium on Computer Architecture, the MIT researchers unveiled a 36-core chip that features just such a network on chip. In addition to implementing many of the group's earlier ideas, it also solves one of the problems that has given troubles for the previous attempts to design networks on chip: maintaining cache coherence or ensuring that cores locally stored copies of globally accessible data remain up to date. The researchers named their chip as SCORPIO. This new 36-core chip is tiled, meaning that it simply repeats the same circuit layout 36 times. Tiling makes multi-core chips much easier to design. In today's chips, all the cores, typically somewhere between 2 and 6, are connected by a single wire called a bus. When two cores need to communicate, they are granted exclusive access to the bus. But that approach won't work as the core count increases. The cores will spend all their time waiting for the bus to free up, rather than performing computations. In a network on chip, each core is connected only to those immediately adjacent to it, and it will provide multiple paths for any destination. However, one advantage of a bus is that it makes it easier to maintain cache coherence. Every core on a chip has its own cache, a local high-speed memory bank in which it stores frequently used data. As it performs computations, it updates the data in its cache, and every so often it undertakes the relatively time-consuming task of shipping the data back to main memory. But what happens if another core needs the data before it's been shipped? Most chips address this question with a protocol called Snoopy, because it involves snooping on other cores' communications. When a core needs a particular chunk of data, it broadcasts a request to all other cores, and whichever one has the data ships it back. If all the cores share a bus, then when one of them receives a data request, it knows that it is the most recent request that's been issued. Similarly, when the requesting core gets data back, it knows that it is the most recent version of the data. But in a network on chip, data is flying everywhere, and packets will frequently arrive at different cores in different sequences. The implicit ordering that the Snoopy protocol relies on breaks down. The MIT researchers solved this problem by equipping their chips with a second network which shadows the first. The circuit connected to this network are very simple. All they can do is declare that their associated cores have sent requests for data over the main network. But precisely because those declarations are so simple, nodes in the shadow network can combine them and pass them on without delays. After testing the prototype chips to ensure that they are operational, the researchers intend to load them with a version of Linux operating system modified to run on 36 cores and evaluate the performance of real applications to determine the accuracy of the theoretical projections. At that point, they plan to release the blueprints for the chip written in the hardware description language Verilog as open source code.